Welcome again. The next speaker of this morning session is Professor Décio Krause from the University of Santa Catarina. And he will speak about I cannot read here, sorry, on the attribution of quasi-cardinals in quasi-set theory. So please, Décio, go on.
Yes, thank you, Fred. Thank you, the organizer, for the kind invitation. And I'm glad to participate of this 10th conference on quantum foundations, because I have participated in some of them, and it's every time very agreeable to meet people in general, in particular people from Argentina. Thank you so much. Yes, my talk today was designed to clear some misunderstandings about a mathematical theory, which is indirectly related to quantum physics, because it is motivated by quantum physics. Then it's called quasi-set theory. Maybe some of you know it already, at least in some details. And we have some difficulties here in order to surpass some criticisms which emerge in the literature. And some of them, or most of them, are due precisely by a misunderstanding of the details of the theory. Then I prepared just a very general talk in order to try to put things in a clear way. And I submit to you, and of course, you be happy in receiving feedbacks and criticism and other criticisms and questionings and so on. Okay, quasi-set theory Q was elaborated to deal with collections we call them quasi-sets of absolutely indiscernible objects, entities, I don't know why. It's postulated that a quasi-set may have a cardinal, which expresses the quantity of elements of the collection. And we call it the quasi-cardinal of the quasi-sets. Then, third one, a quasi-cardinal is taken to be a cardinal in exactly the usual sense of set theories, because they are constructed, the cardinals are constructed in the part of the theory which corresponds to the standard Zermelo-Fraenkel set theory with atoms. Then some criticisms say that there is a dependence on the notion of ordinals in the definition of a cardinal. That is, if the quasi-cardinals are cardinals, then they are ordinals. And they, in attributing a quasi-cardinal to a quasi-set, I am indirectly attributing it an ordinal, hence ordering its elements and consequently discerning them. And this would bring troubles to the original assumption of the idea that the elements would be absolutely indiscernible. Then I will try to explain how this works in the theory now. Below, we shall see some attempts to define a cardinality without relying on discerning the elements of the collection. This is just what I intend to present here. Okay, let's go on. First of all, it's interesting to see how quasi-set theories see these quantities we call quasi-sets. We imagine a quasi-set Q as a tuple composed by Q's, that is K1, K2, and so on, kappa 1, kappa 2, kappa n, which designate the kinds of things. For instance, electrons, protons, neutrons, and so on. And the lambdas expresses the cardinalities of each kind. I give an example. Sulfuric acid can be seen as HSO with the cardinals 2, 1, and 4. Then notice that we are not requiring the distinction between, say, the oxygen atoms. It's enough to have their kind expressed by the theory and their quantities. That's what quasi-set theory tries to express, without individualization of the particular elements. Also, the okay, that's the idea. Then, in saying that we needed to attribute a quasi-cardinal to a set, then I put in blue a supposed quasi-set with two indiscernible things. How to say that we have two there? Well, the usual alternative is to construct a function from the ordinal 2, that is the set of 0 and 1 in von Neumann's approach, to the quasi-set. But it's, of course, we cannot define such a function because you cannot distinguish between the elements of the quasi-set. Then there is a certain trick here. Then my option is to show that we're not doing that. We're not associating to the quasi-set the ordinal 2, but the natural number 2 taken from Peano's arithmetics. That is, 2 is seen as the successor of 0. And of course, this is not a set. Which is a set is the corresponding set in the model of Peano arithmetics, which exists in set theory. But we do not confound the map with the territory, of course. Then that is the elements in the Peano arithmetics, in the formal system, with the elements in its model, or standard model, so to say. Then that's the trick. Define it, at least for finite cardinals, which is apparently enough for doing physics or present-day physics. The finite quasi-cardinals are taken from Peano arithmetic, hence they are not sets. And please do not confound these natural numbers with the finite ordinals of the model of PA there is in the theory, or also called the Peano systems or Peano algebras. Then that's the idea, to take the cardinal from arithmetics. But some people need a careful explanation. Then this is an attempt to explain the details what is going on. The mapping which associates a natural number from Peano arithmetic to a quasi-set in the quasi-set theory, of course, needs to prove to exist. Then how do you prove that such a function exists if the theories are taken in parallel? We need to put them in just one environment. And usually we work with the model of the Peano arithmetic that exists in the theory of sets. Then we are working in set theory, and then the natural numbers are, for instance, ordinals. That's not the way I'm doing things. Are you going to do just the reverse direction? Instead of going from Peano arithmetics for set theory, I'm going from set theory to Peano arithmetics. That is, I take a fact, that is, the language of quasi-set theory is recursive, etc., so it can be arithmetized. We can use the techniques of arithmetization of the recursive languages. So we reverse the direction, going to Peano arithmetics. Let us call Q in quotations the Gödel number of a formula which defines the quasi-set. And we fix an attribution. There is several ways to do that. And then to this Gödel number, which in general is a huge number, we associate a natural number, 5, 3, n electrons, and so on. In the way to associate this natural number to the Gödel number is not, of course, a problem of logic, but physics is a problem of physical theory. For instance, in quantum mechanics, you calculate the quantity of electrons in each orbital by solving Schrödinger's equation. Then you specify the quantity of the elements without individualization. You say that in the first orbital, we may have just 2 electrons. We're not saying that this electron, that electron, but just 2, a natural number, without attributing individualization to the electrons. Then we can see the existence of the mapping from Peano arithmetics to the Gödel number for a particular number which expresses the quantity of elements inside the Peano arithmetics. That's we are going to Peano arithmetics in order to show that this function does exist. Of course, I have done here a remark, just that this works for definable sets because you need to define the quasi-set. But I think that every set considered in physics by hypothesis is to be definable. Okay, that's the trick. So we enlarge the quasi-set theory, show in the title, the quasi-set theory adding p-n arithmetics. That is, I have put in red the primitive symbols of quasi-set theory, and in blue the primitive symbols of the p-n arithmetics, with an emphasis to a predicate k for quasi-cardinal, which will be natural numbers. Then it is standard. Next one, please, Fred. Then you see the elements, the quasi-cardinals, are taken from p-n arithmetics, and they obey the standard axiomatics from p-n arithmetics. This is the standard. These are precisely the first order p-n arithmetics. You can pass. Well, then we can use a terminology. I write in the pair Qn to mean the quasi-set with a certain quasi-cardinal n. This is just a meta-level notation. But we can rewrite some of the axioms of quasi-sets using this terminology. For instance, when two quasi-sets are indiscernible, they cannot be equal because I don't have identity for certain elements in the theory. This is supposed here. But I would say that two sulfuric acids, two molecules of sulfuric acid, for instance, are indiscernible. They are not exactly identical, but they are indiscernible. That's the idea. When they are indiscernible, the answer is that when they have the same quantities of elements of the same sort, the same kind. And this is formulated as above. I think we don't need to read it with details, but just take the idea. Then it's an axiom of extensionality, but in a weaker form. Okay? Then you can go for other axioms. For instance, two quasi-sets having the same quasi-cardinal and being indiscernible, then this quasi-cardinal must be the same. Just structural ones. The second one is perhaps more important. If Z of Q means that Q is a set, a copy of a standard set theory, for all elements, identity holds and so on. Then when a Q, which is a set, has a quasi-cardinal, this quasi-cardinal is precisely its cardinal in the standard sense. Then we recover the idea of the cardinals for elements which obey the standard requisites. In other axioms are just the operational one. For instance, axiom 3. If you have a quasi-set and we have a natural number, then if you have an indiscernible quasi-set, and if this quasi-set indiscernible from Q has some cardinal, quasi-cardinal, then it must be precisely the. And notice that the identity here holds for natural numbers. The other ones are also axioms for structural axioms. Axiom 4, for instance, for each quasi-set and each quasi-cardinal, for all m less or equal to n, there exists a sub-quasi-set with that quasi-cardinal. Then we have 5 elements, then I can suppose the theory is consistent with the idea that we can form sub-quasi-sets with 0 elements, 1 element, 3 elements, 4 elements, and 5 elements. Okay? Yeah, the other axioms are also just structural axioms, saying things which enables us to treat the quasi-cardinal as if they are how they are natural numbers. And just I will not read. I will read just the 8th one, the last one, because this is important for the idea. That is 8 for a quasi-set Q and a natural number n. If Q has n as its quasi-cardinal, then the power set of Q has precisely 2 to n elements. And this is important because please at the next step. This is important because if we have, for instance, 3 elements, n equals to 3, you may reason as if you have one subset with 0 elements, 3 subsets as 1 element each, 3 subsets with 2 elements each, and 1 with the own subset with 3 elements. But the important thing is that, for instance, the 3 with just 1 element cannot be discerned from one another. They are also indiscernible by the weaker indiscernibility extensionality axiom. But you can reason this way, that you can suppose that we have 3 subsets with 1 element each without individualizing them, without counting them. Then let me read here. We can reason as if a quasi-set with 3 indiscernible elements comprises 3 sub-quasi-sets with 1 element each, which turn to be indiscernible themselves. Also, 3 sub-quasi-sets with 2 elements each in the quasi-set itself and the empty quasi-set. So 4 possibilities we have. 4 possibilities: 0 elements, 1 element, 2 elements, and 3 elements. If you regard the distinction among the discernible quasi-sets as something to be as something which can be considered. Okay. Next one, Pat. There is a concept, an important concept in the theory, which is the strong singleton of an element X. I write it as in red, relative to a quasi-set. If X is an element of a quasi-set Q, we denote it that way a sub-quasi-set of Q, which has just one indiscernible from X. The problem is that we cannot say that this only element is X itself, because in order to assert that it is X, we need identity, and we don't have identity. Then we can reason this way because the postulates enable us to admit the existence of this strong singleton. It will enter in the discussion below. Then there is below the explanations. When you write X1, that is a quasi-set, it's important to notice that the variable X is not naming a particular element. It's a generic variable which says one element of the kind X, if you prefer, just one element without individualization. The theory enables us to deal with this kind of things. The next one, please, Pat. So you can reason this way. As Hermann Weil's Ars Combinatoria says, we have 4 visible states. Just one state with 3 elements, with 0 elements, one state with 1 element, one state with 2 elements, and one state with 3 elements without identifying which elements are in each state. Then the theory captures this idea quite well. So I put here the way of counting with this formula in brown. It precisely will give you the quantum statistics. Okay, we can leave this. Then some criticism, but for instance, a very interesting one by Benjamin Janssen. He takes the strong singleton I just defined, the quasi-set of X, which has just one element, and defines a relation X related with Y if Y belongs to the strong singleton. Then he says this provides identity to the X, because if Y must be equal to X. This is false, because in order to say that Y is precisely the element Y, I need identity. And if they are, he says, look, and guesses that since Y and X will belong to all the same quasi-sets of the power set of Q, this defines the identity of X. It's false, because I put here the figure. If we have 3 elements in the Q and the power set there, how can you say that 2 elements belong to the same sub-quasi-set? We cannot identify them. Then we cannot assert, as Janssen has done. This is a misunderstanding of the theory. Okay, then I needed to surpass this kind of criticism. Janssen's claim is false, for it presupposes identity at the start, and yet that X is naming some individual of Q, yet arbitrary, so that if Y belongs to the strong set of X, then y should be x, and so we would have the identity of x. This is Janssen claim. As I told above, epsilon y belonging to the strong signet of x just means that y is indiscernible from x and not that it is identical to x. So y belonging to the strong signet of x does not define the identity of x. When you say that x is any atom, that's an atom, an element to which the identity, the standard notion of identity doesn't apply, and belongs to Q, the only information we have at Q that Q comprises at least one element of the kind X, but without individualization. The atom has, for instance, one oxygen, but not a specific oxygen. There are other criticisms. I think I have some time here. Other criticism, other people insist that the notion of a cardinal is strongly linked to that of identity, so that an attribution of a cardinal to a set where discerning its elements. This may be true for sets in the standard set theory, and still with reservation. Take, for instance, a permutation model in Zermelo-Fraenkel with atoms, also called by some critics. They use these arguments. For our purposes, just Fraenkel's original model is enough. You could say that once any permutation of atoms can be extended to an automorphism of the whole universe, then the atoms would be indiscernible. And I am saying that the permutation models, they say, but inside the atoms in the permutation models are indiscernible. I am saying, no, they are not. They are indiscernible inside the model, but you can leave the model and see that they are different. Okay, the next one, please. Here, they are indiscernible only from the point of view that is inside of the model. From the outside view, identity holds for all objects of the domain. This axiom is acknowledged by Fraenkel himself when he says, before making some atoms become indiscernible. Or look at what Fraenkel said. To show that the axiom of a choice is independent of other axioms, this is the reason he constructed such a model, we shall consider as belonging to a domain B the following objects. First, the null sets, and also the numerable infinite number of distinct atoms, distinct objects. They are different. Then he makes a permutation of these atoms in order they cannot be discerned, and so no choice function can be defined, and consequently the negation of the axiom of choice is true. So apparently there is no chance of being able to define the cardinals without some reference to ordinal. Apparently there is no this alternative. The so-called Scott's trick doesn't rely on the axiom of choice as the standard definition such as von Neumann's do, but on the axiom of regularity and the notion of rank. But rank also depends, the notion of rank of a set also depends on the notion of ordinal, and so the ordinals are reintroduced by the back door. Then we need precisely to find a different alternative. Next one. And also there is another criticism. It's not a criticism of the quasi-set theory, but another attempt recalled by Janssen himself, when he says that Solvaras tries to define a definition of a cardinal independently of well-ordered rings. Then Janssen recalls that Solvaras lays down a set of plausible conditions for a notion of a cardinal in any model of ZF. But look, he's working in a model of ZF. And identity is identity inside the model or outside the model. It does not work too. Any model of ZF prescribes identity for all individuals of the universe, if not inside the model, as for instance the permutation model, but then identity holds outside the model. The most we can do is to confine ourselves within a non-rigid structures, such as Fraenkel's, and play the game as if certain of our objects are indiscernible. But we need to be sure that no one from the outside of the model is looking at us, for she will easily discern the objects and the like. That is, someone outside of the model can see that the elements in the model which are taken to be indiscernible, and this person from the outside can see, no, they are not indiscernible, they are indiscernible. This is a theorem of a standard set theorem. No way. If you are to provide the cardinals to collections of indiscernible objects, as chemistry and quantum physics seem to require, apparently we need to go to quasi-set theory. There is no alternative. We need to. Oh, this is all. I remember here my thanks to Elisa, who has helped me in thinking about these details with kind patience and kind friendship. Thank you, Elisa, and thank you all for listening. Okay, we have time for questions. Fede, you are muted. Fed, you are muted.
Fede está muteado.
Dix has a question. Please go on.
Oi, Dennis.
Thank you, Décio, for your talk. I was wondering about this quasi-set theory. So,
yeah, I know.
So I was wondering, isn't really needed to introduce something complicated like that? Because an alternative seems to be that we speak about, well, let's say, n greater than 1, n quanta in one state, like in quantum field theory. So instead of saying there are n entities, which are indistinguishable and conform to rather strange logical rules, we could just very simply say it's one whole, like what you say in classical physics and also in classical logic. You have so-called mass terms, like a total quantity of, let's say, water or some other continuous substance. And there is no point in it to say, oh, there are actually n liters or other quantities inside which obey some weird rules of logic. So is it not much simpler to do without quasi-sets and to say it's just one big whole? I'm interested in hearing what you have to say about that.
Yeah, of course. I know about your suspicions and criticisms, because perhaps yes, of course, it can be done from some alternatives. But look, Dennis, when you speak about quantum field theory, for instance, Fock spaces.
Yes.
When you say that you have a certain state, occupation number, the occupation number is n, then you just think about attributing n elements without individualization. But it's not true, because you need to work in some framework. And I ask you, where this Fock space is being built? The answer is within quasi-set theory, is a standard set theory. An Hilbert space is as a set. The vectors, the operators, the number operators are also operators acting on sets. Then necessarily in the underground, in the basic mathematics, where you put your Fock space, you discern the things, even if you think that you are not discerning them in the Fock spaces. But this is just a model, a set, a non-rigid structure, if you prefer. But the structure can be extended to a rigid structure. Every structure in set theory, for instance, and Mello-Franco, can be extended to a rigid set theory. And the universe has no other automorphisms than the trivial automorphism. Then all elements are individuals. Then it's okay, you can do things in order to do physics perfectly well without such resources, complicated resources as quasi-set theory. But if you are looking for a philosophical motivation, a foundational motivation, in order to see things working as they were indiscernible from the beginning, not making discernible by artifices, for instance, to taking equivalency relations and so on, if you assume such a kind of metaphysics, so to say, then, of course, standard set theory does not work. And the same thing for mass terms, because if you say, okay, I have a cup of water and I can attribute some quantity of molecules here, and molecules in this water without counting them. But when you represent this cup of water in a set theory, you need to constitute a set. And a set is a collection of discernible elements. Then you are just omitting that the mass terms cannot be discerned. But once they are represented as sets, they become individuals. That's the answer.
So if just to see if I understand you correctly. So on the one hand, you are willing to admit that in physics you can do without the individual elements, but the mathematical theory that applies recognize them as individuals anyway. That's what you're saying. I think about that. Thank you very much.
Yeah, yes. The other question then is just to come is the question I put to Walter before another talk, because if we have a Hausdorff topology or in the space where quantum things live, if this space, the Euclidean space for orthodox quantum mechanics, is a Hausdorff, then any two individuals are ever distinguished because they belong to distinct open balls. Then you cannot speak about indiscernible at all with such a kind of topology. This brings us another kind of problem from the foundational point of view. We needed to think about a different topology too. But this is another question. Thank you for your question. I hope you have understood me a little bit more. To the next.
Thank you very much. Yes, I certainly think I have understood you better.
Thank you. Very kind.
Thank you for the answer. Yes.
Thank you, Dennis.
Are there any other questions in the public? Because if there aren't, I would like to say something about what Dennis asked. I've been thinking about that a lot, but independently, I've been thinking about mathematics and what is the meaning of a set. That's a non-trivial question. Usually, when when people teach about sets, they say, "Well, you have a collection of individual objects." Well, that's true. Yeah, that's the intended interpretation. So you have distinguishable in these individualizable objects of experience. It could be of thought or a bag of apples and so on. But it's tricky because in set theory, you have very huge collections that are infinitely many. And then the standard interpretation becomes blurry, but still you can still think about individuals. And as Décio says, in standard set theory, you are ultimately speaking about entities, wherever they are, that are individuals and can distinguish. But if you change a little bit the actions of set theory, everything changes. So I think that we shouldn't think about the intended interpretation of quasi-set theory as collection of things like tiny particles or whatever they are that have the sole property of being indistinguishable. Why? Because you can change the axioms of quasi-set theory in such a way that even the number of elements is not defined in some occasions. So you can do that. And this is a very strong analogy to what happens with quanta. In quantum field theory, what you have are not tiny particles. I mean, particles appear as a sort of approximation, or it's also a way of speaking. It is a working approximation. You have other thing, which is the quantum field that has excitations. But it turns out that in some circumstances, this quanta can be counted and counted by one. It doesn't mean that you are speaking about individuals. It's like money bank. I mean, whatever it is. So when you deal with these new multiplicities that come, let's call them multiplicity, that come from quasi-set theory, you have a something which is somehow a collection, but not in a standard sense. So in some situations, these collections might have a well-defined number, but in some situations they might not. As it happens with photons in a coherent state of light, you cannot say that. I mean, it's odd to say that a laser beam is a bunch of photons. I wouldn't say that as a physicist. I don't know what you think about that, Dennis. So my position is that we cannot use the intended interpretation of quasi-set theory as if they were like just tiny particles that suddenly become indistinguishable. It's another thing. And it's not so strange because in physics, we are familiar with that idea. We have quanta. I mean, so the model is quanta. So is there any other question in the public?